started the recording. Yeah. So quiz 3, the four functions theorem. This is given to you. You don't have to prove this. But question 1 is the first thing. Okay. So here I have. I'm very happy that some of you found this proof, but not only that, they have argued it very clearly. So who wants to attempt this? Actually, I forgot who. The scores are in my tablet, but I don't want to switch to that screen. But Sneha, do you want to quickly guide me through the steps for solving this question? Sneha? Oh.
Yes.
You can give me the salient points. I'll fill in the rest.
Yeah, well, I considered 4 functions: alpha, beta, gamma, delta.
Correct.
So
alpha,
I considered
beta. You want the definition? Yeah, I want the definition of alpha, beta, gamma, and delta.
So I considered alpha as mu2x fx.
Yeah. So alpha is mu2 times f. Okay. When I write this, that means for all x, alpha x is equal to mu2 of x, f of x. Okay. Alpha is mu2 f. Beta is
mu1.
Mu1. Gamma.
Gamma is mu1 f.
Yeah.
And
so
delta
this,
is mu.
everybody. This is what you have to note. This is not the same. One is mu2 f. Other is mu1 f. Yeah. Delta is
mu2.
Mu2. Yeah. So here also there is a swap. Okay.
Yeah.
And now you have to first check whether we satisfy all the conditions of this four functions theorem. Okay. Which means we have to first check whether this is true. All right. So how would you check if that is true?
So for all x, y.
Yeah. So take any x, y in your lattice. Now alpha x into beta y.
So
first, let's use the definition, right?
Yeah. Yeah.
So that is mu2x f of x mu1 y. Okay.
Now this mu1 y, mu2x,
we can
write
this,
less
right?
than equals to.
So first, let me write it as mu1 y mu2x times f of x. So this, using this star here, we can write it as mu1 times y or x mu2 times y and x f of x.
Oh.
Okay. Yeah. What would be the next step?
Yeah, since f is increasing, so in the next step we can replace fx by f of x joined by.
Since f is an increasing function, we can replace f by f of y, f of something larger. Okay, so y join x is always larger than x, hence this is correct to do. This is because f is increasing. Okay, next step should be to.
Yeah, this is gamma of x join y.
You realize that if you combine these two, right? This is gamma of y of x because of the definition of gamma here. Times mu2 again is by the definition of delta. You can write it as. Okay. So this verifies this condition, but there is one minor thing to do. You can apply this only if all these functions are from L to R plus. Okay. Whereas this here we are not sure whether it is to R plus because here f may be negative. Okay, so we do not know whether alphas and betas codomain, sorry, its range is non-negative. That is a minor fix we have to do. How would you do that, Sneha?
Now that I have made a mistake.
Yeah, I think there you made a mistake.
Yeah.
So I think who wants to tell how you could solve that. Actually, it's straightforward. You have to first let us assume, assume f is non-negative. If it's already increasing, in addition to that, we are assuming that f is non-negative. Then all the hypothesis of the four functions theorem is true, and hence you can now apply this formula, right? Apply the conclusion of this with any, hence the hypothesis or the premise of 4ft is true. Hence, for all x, y subset of the lattice, I can say alpha x, beta y less than or equal to gamma x, gamma x. Okay, I will use the other symbol. X or y delta x means, right? But what will you choose as xn? Here also, I don't know. One of you, I forgot whom. One of you had made a, yeah. Okay, I think I'll pause the recording. I don't want to record your marks. Yeah, you chose choose x is equal to L, but for y you chose something strange, right?
Yeah,
I could not even read what you chose. You said some infimum.
Yeah, I was actually thinking like, since L is a finite set, so if you choose the, infimum of all the elements as y.
Okay. Okay. Yeah, but the easier thing to do is to just choose y also equal to L. Okay, and then you will see what happens. So your alpha, so this essentially we are saying alpha of L times beta of L is, what is L pairwise or L? It's just the entire L, right?
Yeah,
if you take every L, because it contains the each element joined with itself will be that element. So it contains all of L. Similarly, this will be delta of L because L meet L is also L. Pairwise, you can take for every element in L that meets itself would be there. Okay. Now, if you look at Sneha's definition of beta and delta, right? It is easy to see that this is 1, this is 1, because those are probability functions, right? Mu1, beta is equal to mu1, delta is equal to mu2, but mu1 and mu2 are probability functions, right? So, since they are probability distributions, if you add up the probabilities for all the elements in L, in fact, that is what is this overloaded definition of function notation means. Beta of L means essentially you add up the beta value for all the elements in L. That would be 1. Okay, so you will get alpha L less than or equal to gamma L. But alpha and gamma are not just probability functions, they are mu2f and mu1f respectively. So this is sigma some x element of L mu2x f of x, and this is sigma x element of L mu1x f of x. Now this is nothing but the definition of expectation under mu2 of the function f, and this is the expectation under mu1 of f. Okay. So is the argument till this point clear to all of you? There is one more step to do, which is to consider what happens if f could take negative values. But this is in my opinion, this is the key idea. In my key, I had said if you reach this point, you'll give 12 credits. And, so next is actually easy. Now, if f is non-negative, or if f is negative, then you add that bias to f, right? Find an m such that f plus m is non-negative. Okay, find an m. So this would be like you take the negative most value or the minimum of f. And I'm saying minimum because I don't have, this is a finite lattice. You don't have to bother about whether the minimum will exist or anything. It will indeed exist. Take the minimum value and add it so that you get a non-negative function. and notice that E mu2 of F plus M will be less than E mu1 of F plus M because of star. The star applies to all non-negative functions or non-negative increasing functions. F is increasing, so F plus M is also increasing. Moreover, M is chosen such that F plus M is non-negative. Okay, now M is a constant by linearity of expectation. This is E mu expectation of F plus expectation of M. But if M is a constant, then its expectation under any probability distribution is the same, right? I mean, you can even expand it and check using this formula. If F was a constant, it will come out and you will get the sum would be 1. So this is E mu1F plus M. The M and M goes away and you get 1. This is the finishing touch. Any doubts here? Okay. So next, then let me move on. That's an application of this question. Umar, do you want to tell us about your answer? I like your answer for this question.
Yes, sir.
Yeah.
Sir, I defined the lattice as the set of all subgraphs of Kn.
Correct.
And the relation is the subset relation.
Yeah, all subgraphs of Kn with subgraph relation, right? Yeah.
Yes, sir.
Okay.
Yes, sir. For it to be a lattice, every two elements should have a unique supremum and unique infimum, and we can define it as the union and intersection.
Yeah, will be G1 union G2, and your meet will be defined by intersection. Very good. So this defines the lattice.
Yes, sir. Now the equation that is given in the previous question, we have to show that it is
But what is mu1 and mu2?
We will take P1 and P2.
Yeah, it is not P1 and P2. Mu1 is like your Gn comma P1, and mu2 is your Gn comma P2. What does this mean? Under mu1, the probability of any graph is, so mu1 of some, this is a script G. Yeah. mu1 of any given graph G will be equal to what? What would be mu1 of G? If G has M edges.
P1 to the power M.
Correct. P1 to the power M and 1 minus P to the power.
And choose 2 minus M.
And choose 2 minus M. Similarly, this is what we mean by mu1 of G and mu2 of G. This will be P2 to the power M. Right, if G has M edges. So when we say mu1 and mu2, mu1 is picking graphs according to this probability. So neither mu1 nor mu2 need be an uniform distribution. The only case when this boils down to an uniform distribution is when P1 is half. Again, if your intuition is not clear, think about a P1 value which is less than half, like 1/10 maybe, which means sparse graphs will turn out to have much larger probability than dense graphs. Whereas if P1 was much larger than half, then denser graphs with more number of edges will have larger probability than sparser graphs. In some sense, even though this probability distribution is not uniform, but restricted to graphs with the same number of edges, they have the same value. So the bias only looks at the total number of edges in the graph. Okay? So that is how you should build an intuition about what this G and P1, G and P2, etc. is. Okay. So this is what I am trying to say, why I said this looks obvious after 2 minutes of thought. So you should, like if P2, since we are given that P1 is a larger probability, it should be clear that, okay, P1 favors more, rather than P2, P1 favors slightly more denser graphs. There is more probability of picking a denser graph under mu1 rather than mu2. Okay. By the way, both P1 and P2 may be less than half. So I'm not saying, in an absolute sense, I'm only comparing between a random choice made according to the distribution mu1 versus a random choice made according to the distribution mu2. Between them, mu1 has a slight tendency to pick denser graphs than mu2. And since chromatic number increases with density, that's why I kind of said it looks obvious, okay? Because if you are tending to bias towards denser graphs, then the chromatic number, or at least its expected chromatic number, can only go up. Okay, so that is the hint part. Yeah. But now, Umar, you can continue.
Yes, sir. For the two graphs x and y, we have to show mu1x, mu2y is less than equal to
yes. So we have
mu1x join y, mu2x meet y.
So we have to let me just call that graphs as G and H. Okay, because they're more common name. Let G and H be any elements of the lattice. Right, your lattice you have already defined all subgraphs of A. Right?
Yes, sir.
So how will you show that? You need to show that this is less than mu1 of G meet Y and mu2 of G. Sorry, I get it wrong. Yeah, this is correct. X or Y, X. Yeah. So how will you show this?
Yes, sir. So join and meet will be union and intersection.
Correct. So this is actually to show that. Yeah. So this is equal to mu1 of G union H, mu2 of G intersection H. Now I really like the way you argued this in the answer sheet. So you can tell us that.
Yes, sir. For an edge, we will have 4 cases. Edge belongs to G and H both.
Yeah. For any edge E, element of the edge set of Kn, there are 4 cases to consider.
Okay. Yes, sir.
So
Edge
what are they? Yeah.
To both G and H.
Yeah. So E is in both G. Okay, let me write it as EG intersection EH. Okay, then what happens? What happens to the left-hand side? What happens to the right-hand side? Okay, or you maybe you should go by what you had written. It is cleaner than what I had thought.
Side P1, P2. And
so here the LHS will have P1, P2 because E is in G, so it's a P1, not 1 minus P1. E is in H, hence it is not, hence it's a P2. And RHS will have
RHS will also be P1 and P2 because it is in both union and intersection.
Yes, RHS will also be P1 and P2. So this is in fact equal to. We only have to prove that this is less than or equal to. But the contribution due to this edge is in fact equal in the left-hand side and the right-hand side.
Yes.
Okay. And now second case is
E1 not in G, E1 in H.
Yeah. Oh, okay. Sorry, I wrote the other one. It is in G but not in H.
Okay.
Then what is in the LHS?
P1 multiplied by 1 minus P2.
Correct. And what is in the RHS?
P1 1 minus P2.
Yes.
Same.
P1 because it is in the union. No, but it is not in the intersection, right?
Yes, sir.
So how did you?
P1
it is in the intersection, but
union.
not. It is in the union. Correct. So this also becomes an equal. Right?
Yes, sir.
Now third case is symmetric to this, right? EH minus EG. So this will be 1 minus P1 times P2.
P2.
And here it will be
P1 multiplied by 1 minus
1
P2.
minus P2 because it is in the union. So P1 comes because of this mu1 here. P2, 1 minus P2 comes because under mu2, it is not integral. Okay. So this, how do you show that? You want to show that the left-hand side is less than or equal to the right-hand side.
So we will multiply and P1, P2 will get cancelled.
So this that 1 minus P1, P2, and this is P1 minus P1, P2. So this goes away. So this is a comparison between P2 and P1, but we already know that P2 is the smaller guy. So this is the correct direction. And the last case is when E is not in E of G. E is neither in E of G nor in E of H. In this case, the left-hand side will be 1 minus P1, 1 minus P2. Right-hand side will also be the same. 1 minus P1, 1 minus P2. So in fact, it is an equivalent. Right? So yeah, Uma's argument is that since for each edge, right, for each edge, the left, so for all edges in Kn, your contribution of E to LHS is less than or equal to contribution of E to RHS, and everything are, I mean, all of these are non-negative, in fact, positive quantities, right? So this means LHS is less than or equal to RHS. There are other ways to do. I mean, you can do some term-wise rearrangement and show, but I think this makes it, Umar's argument makes it very clear. Okay, you split cases for each edge and see that only in one case, in fact, there is a less than or equal. In all the other three cases, in fact, it is equivalent. Okay, so this tells you that this condition is satisfied. Yeah, the requirement is satisfied, and hence yeah, so hence Umar will conclude that E. Okay, now what is F?
Sir, F is X is F.
Yeah, so F of X is nothing but the chromatic number, right? Chromatic number of graph G. So, but in order to apply the question 1, we have to show that F is an increasing function.
Yes, sir.
So why is F increasing?
Sir, because if we have a graph G and its chromatic number is K,
Yes.
then
correct. So what you are saying is that if G1 is a subgraph of G2, right, then F of G1 has to be less than the chromatic number of G1 has to be less than or equal to chromatic number of G2. Very easy way to see that, take any optimal coloring of G2, that's also an optimal coloring of G1.
yes, sir.
Yeah, because G1 can only have fewer edges than G2. So any proper coloring of G2 is also a proper coloring of G1. Hence the chromatic number can only be equal or lower. This proves that F is increasing, and hence everything is now in place. Expectation under mu2 of chi is less than or equal to mu1 of chi. Okay, very good. Any please feel free to stop and ask if any point was not clear, because these two questions, I think only around 4 of you have satisfactorily answered. Okay, so others, I'm hoping, if you have any confusion, you will ask me now.
Sir, how will we give the final result? Expectation under P2 is less than expectation under P1.
This is only a matter of notation, right? This because this P2, we have defined it to be XP be a random variable which equals to a chromatic number of a graph sampled according to GNP. So that's exactly what this says. Okay, this is the same notation. E mu1 is same as EP1. It's only a matter of notation.
Okay.
Right. Okay. So question 3, I think almost most of you have got it correct. Okay, I don't want to spend time here. You expand the Taylor series and then compare term by term. The crux is essentially in proving that 2n factorial is greater than 2 raised to n times n factorial. These terms will come in the denominator. That's the only difference between these two expressions. So if you can prove that, then this is done. Okay. So in the interest of time, I will skip that and go to the next question. So Vishnu, I think your answer was the most satisfactory for this. You want to guide us, give me the key steps?
Yes, sir.
Yeah.
Sir, we have given that sum of the Bernoulli random variable.
Ah.
Then it is also a Bernoulli random variable, because we know that the sum of the Bernoulli random variable is the Bernoulli random variable.
No. Yo. No, that's not correct. Sum of Bernoullis is what is known as binomial. Okay, a Bernoulli random variable only takes two values.
Yes, sir.
Okay, whereas even if you have two Bernoulli random variables, let's say x1 and x2, x1 plus x2 can take, so even if x1 is, let's say, plus 1 minus 1, x2 is also plus 1 minus 1, your x1 plus x2 can take minus 2, 0, and 2, right? So that's no more a Bernoulli random variable. Okay.
Yes, sir.
In fact, the sum of 0, 1 Bernoullis is what is known as the binomial random variable, and so on. Okay, so that is, yeah. So, but that's only a problem with the name. Don't worry about the name. Okay. So, but
Yes,
first tell me, like, what is E of xi and sigma of xi? Anyway, we will use it later, right? Sigma squared of xi, the variance of xi and.
Yes, sir. E of xi 0
0.
and sigma of xi, sir. I think I made a mistake here.
Yeah.
I wrote 1 by n square summation of I to n to p 1 minus p.
No, first of all, there is no p here, right? Because we are given half and half probability, right?
Yes, sir.
Huh.
I was confused, sir, so I wrote the directly formula. I didn't do. I didn't.
Yeah, but let us calculate it. Okay, so this is half times plus 1 squared, because anyway mean is 0, so I can just take the second moment, minus 1 squared. So this is half times 1 plus half times 1, which is 1. Okay, so some of you have made a mistake of writing it as 1 by 4, I think, by using the formula p into 1 minus p.
Yes, sir. I also did the same firstly. Then I
but that is for the 0, 1 Bernoulli, not the plus 1 minus 1 Bernoulli. Okay.
Yes, sir.
Yeah. So now we have this. Next question is, what is E of x and what is sigma squared of x? Where x is this guy, where x is the summation of x1 to x.
So then I try to find out with a moment generating function. The first moment generating function is the Ex, and the second moment generating function is the sigma square x variance. Then I go with a basic definition of a moment generating function. Expectation of e की power sx.
Okay.
Then try to calculate.
Okay. No. So anyway, here E of x would be just by linearity of expectation. It would be E of xi, summed over 1 to n, that is 0. Here, this is just linearity of expectation. And here, because we have independence, okay, in fact, we only need pairwise independence, but we are given mutual independence. Because we have independence, the variance adds up and becomes n. Okay, 1 plus 1 plus 1, n times you have n. And what we have been asked to show is something like probability that x is greater than alpha sigma. Right. So let's at least analyze first one side of it. Alpha sigma. This is equal to probability that this is where Vishnu's moment generating function happened. Expectation of e raised to lambda x is what is the moment generating function. But we need not use that terminology. We can directly compute this, right? So this is because e raised to lambda x, for any lambda for all lambda positive is an increasing function. So in order to compare two values, you can substitute that values inside of any increasing function and then say that the function value is larger than that. Okay. But for this, we can use the Markov's inequality, because this is, I can write it as expectation of e raised to lambda x e raised to, this will become the constant, e raised to lambda x times expectation of e raised to lambda x. I'm just multiplying and dividing by e raised to lambda x, which now by Markov's inequality will be at most 1 by this guy. This guy is the constant now. So 1 by that, which would be e of e raised to lambda x by e raised to alpha sigma. Okay, so this is, let me call it 1, and let me analyze the numerator of 1. Expectation of e raised to lambda x is half times e raised to lambda plus 1 plus half times e raised to lambda minus 1. Okay, so this is why we have the question 3 here. So this is e raised to lambda plus e raised to minus lambda, but there is a half, so this 2 will go away. You will get e raised to lambda squared by 2 as an upper bound for that. Okay. So this is upper bounded by e raised to lambda squared. For any lambda, and hence your 1 would now become the probability of the event that we are looking for. Probability of x greater than alpha sigma is upper bounded by e raised to lambda squared by e raised to alpha sigma. Okay, so I think here I only needed lambda equal to 1, right? Is that true? What should I? Did we make e raised to lambda x? Sorry. Okay, this is not for numerator of 1. This is for some lambda xi. Okay, so that does not completely. This is e raised to upper bounded by e raised to lambda x, right? So your e raised to, this is by independence. Since you have independence. Okay, first let me write it as e raised to lambda sigma xi I equal to 1 to n, which becomes e times pi I equal to 1 to n e raised to lambda xi. Now, because of independence, I can write it as pi equal to 1 to n e raised to lambda xi, and hence this is all the same for all of them. So this is e raised to lambda xi the whole power n, which each of them is bounded above by e raised to lambda squared. So this will be e raised to lambda squared n. Okay, so now let me substitute this into 1. Now 1 becomes probability that x greater than alpha sigma is at most e raised to lambda squared n by e raised to alpha sigma. Yeah, and so what is sigma? Sigma squared is root 10. Sorry, sigma squared is n. So this is equal to e raised to lambda squared n minus alpha sigma. But since your sigma is root 10, let me write this way. And now we have to find the best alpha. So this, let me call it as equation 2. Now optimize for lambda. So your dou by dou lambda of lambda squared and minus. Okay, there is getting confused a bit because alpha does not have any dependence on lambda.
That I also stuck here because I changed the variable.
This is
Hello.
Okay. So I made a mistake here. I should have write it in another color. Since I'm taking e raised to lambda x, I should have taken e raised to lambda alpha sigma. Okay. So this should have been e raised to. This is correct. Yeah. Here there is a lambda alpha sigma, and that will go here also e raised to lambda alpha sigma. And here also there will be a lambda alpha sigma, and there will be a lambda here. Okay, sorry for the confusion, but I thought this was a very easy question. Okay. So now now I'm ready to differentiate this. This is 2 lambda n minus alpha root n. So if I set this to 0, what I will get is alpha is equal to 2 lambda n. Sorry, I have to solve for lambda. Lambda is equal to alpha root n by 2n, which is equal to alpha by 2 root n. Okay, this is the lambda that we will substitute to 2. So this, if I call 3, then 3 in 2 will give me that the probability that I'm looking for alpha sigma is at most e raised to lambda squared n. What is lambda squared? Alpha squared by 4n times n minus alpha minus lambda alpha root n. So lambda alpha is alpha squared by 2 root n, and there is a root n. Root n goes, n goes alpha. So this is equal to e raised to alpha squared by 4 minus alpha squared by 2, which is equal to e raised to 1 squared by 4, right? Did I get the question wrong? Why did I put a 2 here? Or was it a root 2? And did I make a underscore? Okay. What am I doing today? And why are you not pointing out any of these? Right, because the bound that we have here has this lambda squared by 2. Okay, so, yeah, so here there would be a by 2. Here there would be a by 2. There is a by 2. Here also there is a by 2. So this goes away, this goes away, this goes away. Yeah, so this becomes lambda squared minus alpha squared into n. Yeah, there is a by 2 here, and there is nothing here. By 2 here, 1 here, and this is a 2. Okay, yeah, I have made it extremely ugly, but yeah, the point is not the details. Okay, the opposite side is also same. In fact, in this case, the random variable is symmetric. The probability distribution will look the same on either sides of the origin. Okay, so the other side will also give you a similar minus alpha sigma will also give you the same. Okay. So another reason that I had put in this bound, is that you get a direct comparison with what Chebyshev would give you. Okay, Chebyshev in this case would have given here x minus mu, but the mu here is 0, so it is probability of x minus mu is just x greater than alpha times sigma. Chebyshev would have only given you 1 by alpha squared. Okay. Now, in this particular special case of a Chernoff bound, you can make a comparison between 1 by alpha squared and e raised to minus alpha squared. Okay. So that's the the difference that Chernoff can bring. Okay. Any doubts here? Yeah. Okay, we are at 9:48. Should we move on to the other quiz? Okay, what I'll do is, for the second quiz, if you have any doubt, then we can discuss that. Yeah, so here again, or let me make a few comments about what are the common mistakes that many of you made in quiz 2. I'm sorry that I corrected it so late. I should have corrected it then. If I had done that, then it would have been, fresher in your memory. But yeah, I could not do that. So here, if you use anything weaker than the LLLV3, okay, you will not get this answer. Okay, in fact, that is why this LLLV3 is the true asymmetric Lowash local lemma. Anything other than, like, if you had used LLLV2 or something, you make some kind of a mistake. Okay, so those who did that, please go through that again and also compare it with. Okay, there is a long delay in the screen getting updated. Compare it with your answer. Then question 2, almost all of you have got it correct. But one answer I really liked was from Lalat, who used the convex combination idea to, I think, establish this one. Right? Okay. Now, Lalat, can you recall what was it? How did you? I don't insist that you recall because I know it was long ago. But do you remember this? How you showed A bar as?
So even I don't remember, like somewhere it came up and then I just, so there's that connection because P and 1 minus P is there. So like that just gives this combination.
Correct. But that was, when I actually read it, I thought that was a nice idea. It could have more applications. So that aim is to show.
Yes, even I tried multiple times. Couldn't solve. Then I thought, oh, this was the like that just clicked that time.
By the way, there is a very straightforward solution that you will get if you just expand and play around. But that's what most people have done. But your solution was different. So okay, let me try to, okay, I'll write the aim and then I'll try to work. We want to show that P of A bar given B is larger than or equal to, negatively dependent. So this is less than or equal to P of A bar. If I remember Lalat's argument correctly, and if we are working backward, it was like showing, show that PA is, or maybe, okay, or maybe I think it was about the next problem. Okay, that is why A bar B. Okay, and we are, what is given?
The second part, I think.
Yeah, I think it was for the second part. We are given that P of AB, since it is positively, by the way, here it was, in this exam, it was all strict positive and strict negative. Yeah, so what finally Lalat showed was that PA is a convex combination of these two guys, P A given B and P A given B bar. So once you show that, something is a convex combination of two guys, that means this is the picture. Okay, this is one of them. Okay, in this case, this is P of A given B. This is P of A given B bar. And if your P of A is a convex combination of these two, and one of them is larger, the other has to be smaller. Okay, that was the final nail in Lalat's argument. I really like that. But how could we, then how
the expression was something like this. So there's like P of A equals to P of B into P of A given B
P of A equal to, can you please say that once more?
Yeah, P of A equals to P of B plus into P of A given B plus 1 minus of P of B.
Correct. Yeah.
Into P of A given B bar.
A given B bar. Okay. Yeah, correct. So this is the total probability rule, right? You have a event A here, right? And then you want to calculate P of A. But now let us say you have an event B, and yeah, let's say this is your B. This side is B. Then what you are saying is that you can write your P of A as P of A intersection B plus P of A intersection B bar. But this I can write it as P of A given B times, okay, let me write it in the opposite order. P of B times P of A given B plus this is P of B bar given P of A given B bar. And this P of B bar is what is written as 1 minus PB. Okay, since PB is a probability, it is between 0 and 1. This PB and 1 minus PB qualify to be the coefficients of a convex combination. Okay, so this was the answer that Lalath had given. And I tried sometime to see if the same idea you can apply to the other questions, 1 and 3, but I don't think I got it. This is a very nice trick. By the way, this is not the standard way to do it. Most of you have done it in the standard way, where you could kind of carefully expand the expressions and find it. Okay. In question 3, so here again, I won't even go into the details because the proof of the Lowash local lemma is involved. The only remark that I want to say is that actually you will end up using this not just in the induction step. There is one place in the base case also where this is important. Okay, it is in the scenario where your conditioning family does not have anything on which I can potentially depend. So that mistake some of you have quiz 2. That mistake some of you have made. Yeah. Otherwise. Okay, but I also see that question 3 is, very few people have answered it correctly. And question 4, actually, I thought a lot of you would answer. Okay, question 2 was something very similar to that tutorial question that we could not solve about a cycle. Okay, in which I think there were 4 vertices in each color. Right, this was a very question similar to that, but with much more room so that Lowash local lemma would work. Okay, so here many of you have got the experiment itself slightly wrong. I'm not saying using other experiments you cannot prove it. You may be able to prove it, but the natural random experiment to consider is pick one vertex from each color independently and uniformly at random. Okay, so you have k colors, so you will end up picking exactly k vertices. Okay, so one vertex per color you would pick. So that all automatically satisfies the condition for the independent set that it contains at least one vertex of every color. Now, what may or may not be satisfied is the other condition, which is that this is an independent set. Okay, and now you analyze the probability that so this is your random experiment, and your bad event X is bad event AI is the event that ith edge. Okay, so let me just number the edges in the whole graph as some E1, E2 up to EM. Event that the ith edge lands in this chosen set, call this set as I, lands in I. So P of AI would be, for a set to land in this, you should pick this vertex, but there are at least how many L vertices, right? L vertices, at least L vertices for each color. So there are at least L such vertices of the same color, and here also there are at least L such vertices of the same color. So the probability of picking this guy is at most 1 by L. If there are like 2L vertices, it would be only 1 by 2L. Similarly, picking this vertex is also at 1 by L. So this probability is upper bounded by 1 by L squared. And that dependency degree, right? Your dependency degree, like when you pick the sets, what are the events you can potentially influence? You can potentially influence any edge which has one endpoint in this color class. Okay, even things like this, right? So that if you count, it would be okay. But here, so maybe I'm making a mistake, a small mistake here. Maybe before doing this experiment, I will delete some vertices so that each color class, each color has exactly L vertices. Okay. Otherwise, I think when I come here, I will need the wrong kind of inequality, which means this is equal to. Okay. So the dependency graph is now at most twice L delta. Okay. I mean, we can save a delta minus 1 or something, but it is at most 2L delta. So your EPD will be like E times 1 by L squared times 2L delta. So this is 2E into L squared, 2E into delta by L, but L is at least 8 delta. So this is 2E by 8, which is less than 1. Okay, so that's the idea. The other kind of, yeah, but if anybody wants to discuss another option, that also we can do. I think Sneha wrote it this way. Yeah. Rajesh also had almost, but Rajesh is not here today, right? That's why I did not ask. Rajesh also, I think, got the same idea. Maybe towards the end, he made some small mistake. But do you want to discuss any other option if you have time? That is, otherwise you're free to leave if you have another class right now.
Sir, I think what I don't exactly remember what I did, but I didn't. Okay, what I had tried was like the events being that between a pair of colors there is an edge.
So your now your events are there are k colors, right? So k choose 2 events, right? K choose 2 events. AI is that there exists an edge between color I. Okay. Aij is an event that color I and color j. But your random experiment was the same, Abraham. Do you remember?
Choosing a set of k vertices, one of each color.
Which essentially, okay, but that's not a complete specification. We should say whether it is
independent.
Two things.
Okay, no, not independent.
Within both, within the same color. So, is it uniform? Right, that's one question. And then after you have made choice for one color, when you go to another color, maybe somebody can greedily try to optimize by only picking a vertex which does not have an edge to the guy already chosen. Then it is no more independent. So you need both. You need uniformity as well as.
Yeah, from each color it is uniformly taken and it's independent.
Correct. But now that I think about it, I think you made some statement which says the dependency graph is kind of not there. You said that the positive dependence of one event is only on itself. But I don't think that is justified even in this model, right? Because if you but again, this positive dependence we have to really formally argue. But I could when I was correcting, I thought I had a counter example to that claim. What are two events? So Aij is the event that there is an edge between color class I and J. Correct. So now suppose, this is from color class I, this is from color class J, right? Now this J had a, okay, but there is also, like, we really do not pinpoint a vertex, but this kind of, you know that now for another edge which is attached to J, the probability that that edge also comes in increases. Okay. So for example, what I'm trying to say is that suppose that this graph, is it given it is a uniform graph? Yeah, we're not given it's a uniform graph, right? N vertex graph. So suppose you know that you pick a very high degree vertex, then that influences, that makes both this, that is from J, color class J, then that makes two events more likely, their intersection. But again, I mean, what I'm only arguing is at the level of an intuition, because unless you formally write out, your event Aij is a very complicated event. Okay. Even what is the probability of Aij?
That I got delta by L. I'll check my notebook. I must have drawn something.
Yeah, the delta by L, you are only looking from one side. Okay, I think you are thinking, okay, let us now pick any vertex from one color class. It has at most delta neighbors, but here you have a total of L vertices in the second color class. So therefore, you can bound it by delta by L. Okay, but again, think about that. So you see that this delta has come in. So this delta will now also influence your, if this is your I, this is your J, it will also influence your K if you are freezing on this. Right, but also the probability of this will also depend on each thing. But anyway, think about it. If you find a justification for your argument, you can tell me that next time we meet. Okay. Now I think it's we have exceeded the time. Okay. So